Welcome to the Intel Quartus Prime Software Design Series Timing Analyzer Online Training Part 4 Required SDC Constraints. My name is Steve. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you're done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. In this course, you will learn how to perform timing analysis in the Intel Quartus Prime software using Timing Analyzer. You will use Synopsys design constraints or .sdc files to constrain a design to meet timing requirements and to compare results. You will learn how to generate timing reports in Timing Analyzer and gain familiarity with its graphical user interface. Here is the agenda for this course. In previous parts, we looked at basic timing analysis concepts and the terminology used in Timing Analyzer. This included a discussion of the terminology used to select nodes from the SDC netlist for targeting timing constraints. You were then introduced to the Timing Analyzer GUI, its general use, and how to incorporate the tool into the Intel Quartus Prime design flow. The third part ended with a look at Timing Analyzer's extensive reporting features. In this final part, we'll discuss the SDC constraints required to fully constrain a design, as well as a number of optional constraints. To finish up this training, let's look at the constraints you'll need to fully constrain your design. The first and most important constraints you must create are clock constraints. Clocks in the Timing Analyzer are not actual physical locations in the design. They represent signal characteristics applied to a point in the design. There are two major types of clock constraints. The first type are absolute or base clocks. These are clocks that are typically input on the device's clock pins. A variant of a base clock is a virtual clock. A virtual clock is a clock that drives devices the FPGA communicates with, either on the FPGA's inputs or outputs, but never actually enters the FPGA device. However, a virtual clock's properties must be defined in the .sdc file in order to establish the correct launch/latch edge relationship for an I/O timing analysis. We'll look at virtual clocks in more detail in a moment. The second type of clock constraints are generated clocks. Generated clocks are internal FPGA clocks that are based off of a base clock or some other generated clock. There must be a defined relationship between a generated clock and its source clock. A good example of this are the clocks output from a PLL. These clocks are related in some way to the input reference clock of the PLL. A generated clock constraint is used to define that relationship. By default, all clocks are related to one another and all cross-domain transfers are analyzed by the tool, even if those clock domains are asynchronous to each other. It is possible to separate clock domains using special constraints called timing exceptions. We'll touch on these special commands later. Here is the create clock command that you would use in the console or in a .sdc file to define the properties of a base or virtual clock. While the clock period is a required argument, a clock name is optional. You can give the clock a unique name to make it easy to identify and use in other constraints or reports. If you don't supply a name, the clock will be named after the node targeted by the constraint. The -waveform option is used to specify the rise and fall times of the clock to create phase-shifted and non-50% duty cycle clocks. By default, clocks in the Timing Analyzer rise at the start of the period and fall at the halfway point. The -add option is used to apply more than one clock constraint to a particular target location in the SDC timing netlist. This may occur, for example, if either a 50 MHz or a 100 MHz clock is applied to the same clock input pin of the device due to external control logic or a board build option. Finally, the target option is used to select where the SDC netlist to apply the clock constraint. This will typically be an input port in the netlist accessed with the get ports collection. If you don't supply a target, the clock is considered to be a virtual clock driving some other device on the board. Virtual clocks are used with I/O constraints and the timing analyzer itself to automatically derive I/O-related timing uncertainties. We'll look at the creation of virtual clock in a moment. Here's the same constraint accessed in the Timing Analyzer GUI, either in the Constraints menu in the main Timing Analyzer window or the Insert Constraints submenu under the Edit menu of the SDC file editor. You can set the same parameters as with the actual command. The clock waveform graphic updates as changes are made to the settings. The SDC command field near the bottom updates as you make changes as well. This is a great way to start learning the SDC syntax. If you don't know the exact target you should use, click the Browse button to open a tool called the Name Finder. The Timing Analyzer Name Finder is very similar to the Intel Quartus Prime Node Finder. The difference is that the Name Finder is designed to search the SDC netlist. Select a collection from the list at the top and use the filter to search for only specific items in the collection. The highlighted options are used to decide what part of the SDC netlist hierarchy to search. When the list button is clicked, all the items in the selected collection that match the filter are listed on the left. The arrow buttons in the center move items to the selected items list on the right. As you select items from the netlist, the SDC command field at the bottom updates as well. You can edit this field, putting in wildcards to simplify the command. For example, if you wanted to target the entire DNA bus, you could use a wildcard by editing the SDC command to add DNA star. Clicking OK returns the main constraint entry dialog box with the selected collection and items filled in the target field. After creating base clocks, you'll need to create constraints for any generated clocks in the design. You do this with the create generated clock command. Most of the arguments here are used to define the relationship between the source and generated clocks. Some examples are inverting the generated clock with respect to the source or performing a phase shift of the generated clock a certain number of degrees with respect to the source. A source clock is required for the generated clock constraint using the -source argument. Typically, the source should be as close as possible to the generated clock. Going back to the example of a PLL, the source of any clock output from the PLL should be the reference clock on the input pin of the PLL. If there are multiple clocks at the source location due to the create clock -add option, use the -master clock option to select the correct one. Finally, the -edges and -edge shift options can be used to define a relationship with the source clock based on the rising and falling edges of the source. This is a different way of defining the relationship and may be useful if the relationship to the source is not easy to define with any of the other methods. Here is what the GUI looks like for creating a generated clock. The generated clock can have its own unique name, just like a base clock. Select the source clock location and the target location using the name finder. Then use the options available to define the relationship between the source and the generated clock. You can see here in the targets field how the SDC netlist hierarchy targets specific pins in the netlist. In this case, a PLL's output clock pin. If a clock name is not filled in at the top of the dialog box, the generated clock will be given the same name as the target. Since the target name can get quite complicated due to the SDC netlist hierarchy, it is recommended to always give easy to identify names to generated clocks. Here is a simple example of how to create base, virtual, and generated clocks. A clock comes into the design on the clock in port and goes to the clock input pin of the register name inst. The first create clock command defines the base clock to have a period of 10, targeted to the clock in port. Because no name was given to the base clock, its name will be the same as its target, which in this case is clock in. This is the name used when referring to the clock in other constraints. Notice that there is a second base clock constraint. This second clock has the same period as clock in, but no target is included in the constraint. This is an example of a virtual clock constraint. The virtual clock, named clock invert, is not used anywhere in the FPGA design. However, it is recommended that for each base clock in your design, there is a corresponding virtual clock which may or may not have the same properties as the base clock. In this example, clock invert is an upstream clock, meaning it drives some external device that sends data to the FPGA, and it happens to be the same clock as clock in. When performing an I/O timing analysis with these clock constraints, clock invert will be the launch clock and clock in will be the latch clock. Adding the extra virtual clock in this manner will also let the timing analyzer automatically add I/O timing uncertainties using a command we'll look at in a moment. This can help in performing a timing analysis that more closely reflects real-world timing. To finish constraining the clocks in this design, the create generated clock command defines the generated clock at the output pin of the clock divider. The generated clock is named clock div. Notice that the source is assigned by using the getPins collection and the clock pin of the int cell. The source is set to the input pin of the register, the closest point to the output. However, in this example, you could use the clock in I/O port as the source to generate the same clock because there is no logic in between. The divide by option defines the relationship. The end of the command selects the target. Again, the getPins collection is called and the Q output pin of the int cell is selected. All clocks in the simple design are now fully constrained. As a shortcut to creating generated clocks on the output of PLLs, you can use the Derive PLL clocks command, either added to the .sdc file manually or using the GUI dialog box. This is an Intel FPGA SDC extension that automatically creates generated clock constraints for PLLs based on the parameter settings specified when the PLL was added to the design as an IP core. Even if the characteristics of the PLL change, the generated clocks will update automatically to account for these changes. The only requirement for this command is that the input clock of the PLL is already constrained. However, if the PLL input clock is not constrained, you can use the -create base clocks option to automatically create the associated input clock, again based on the PLL settings. If you need to translate this command to standard SDC, use the -expand option with the write SDC command. This will replace the Derive PLL clocks command with the standard create clock and create generated clock constraints. To access the Derive PLL clocks in the GUI, simply go to the Constraints pull-down menu in Timing Analyzer and select Derive PLL clocks. Here is an example of how the Derive PLL clocks command can simplify PLL output clock constraints. On the left are the constraints required to fully constrain the PLL shown here. First, the input clock is constrained as a base clock. Then, 3 long create generated clock commands constrain the outputs of the PLL, setting the source and target locations as well as defining the relationships to the source. These 3 commands are replaced by the single Derive PLL clocks command on the right. It's easy to see how this can help when there are multiple PLLs in your design, each with multiple output clocks. The one caveat to the Derive PLL clocks command is that there is no way to select a custom name for the generated clocks that you normally would with the -name option. The clocks created with the Derive PLL clocks will use the target pin name, which could be unwieldy if the generated clocks must be used for the other constraints in the design. As a workaround, use the -expand option with the write SDC command to expand out the Derive PLL clocks command to standard generated clock constraints, and then add in the -name option to the standard create generated clocks commands to name the clocks. The clock constraints discussed so far define clocks that are perfect square waves that do not take into account any external delays that may be present outside of the FPGA. To provide more realistic clock characteristics to the timing analyzer, special constraint commands can be applied to clocks to adjust how the timing analyzer performs its analysis. First, the set clock latency command is used to define source latency on input clocks. Source latency refers to board-related delays that may be present on input clocks that could cause these clocks to arrive earlier or later than expected. Clock latency can be applied to any clock input to the FPGA device. A good example of where set clock latency is used would be for a feedback clock. The delay on a clock path that is output from the FPGA and then returns to a clock input pin is unknown by the tool. Using the set clock latency constraint makes it easy to define this delay. The next special clock constraint is Derive clock uncertainty. This command is an Intel SDC extension that can automatically derive uncertainties inherent in clocks used in supported devices. It adds uncertainty for data transfers within a single clock domain and for transfers going between two clock domains. As discussed earlier, uncertainty values can be added to the setup and hold data required time calculations to essentially make the timing analysis more pessimistic. The Derive clock uncertainty command is an easy way to add clock uncertainties without having to define them manually throughout the device. While Derive clock uncertainty always derives internal device uncertainties, a virtual clock is required, as discussed earlier, for the command to correctly derive uncertainties on data I/O. It is recommended that the Derive clock uncertainty constraint be used in all designs to provide the most accurate timing analysis. Finally, the set clock uncertainty command lets you manually add uncertainties to model jitter, guard band, or skew. This can be used on its own or alongside Derive clock uncertainty to completely customize uncertainties throughout your design. For more details on the usage of these other types of clock constraints, see the Timing Analyzer chapter in the Intel Quartus Prime handbook and the built-in help. The Timing Analyzer considers all signals on device clock input pins and all signals that are used on register clock inputs to be clocks that need to be constrained. To verify whether you have constrained all the clocks in your design, use the Unconstrained Paths report found in the Intel Quartus Prime compilation report or generated in the Timing Analyzer interface using the report UCP command. Here is a typical Unconstrained Paths report. Selecting the Unconstrained Paths summary report indicates the number of unconstrained clocks. Selecting the Clock Status Summary report lists the signals considered to be clocks by the Timing Analyzer. The report indicates whether these clock signals are constrained or not. Any unconstrained clocks need to be constrained for a complete analysis. Along with clocks, I/O paths must also be constrained. Internal path timing is understood by Timing Analyzer, but the tool has no information about I/O paths. You can constrain I/O paths in a number of ways. This first method is useful if I/O signals simply go through combinational logic in the design. In this case, you can use the set max delay and set min delay constraints to specify an absolute delay range that signals would take when going through the logic. The set max delay and set min delay constraints both have the same options, allowing you to specify the paths where the delay should be applied. For this method of constraining I/O, use the -from and -to options to select I/O ports from the Get Ports collection. In general, -from and -to can be used to target any items in the netlist as the source or destination. The other options listed here can be used if the delay should only be applied on the rising or falling edge of the source or destination clock. Here is the GUI interface for creating a set min delay constraint. Use the name finder to select the end nodes of the path where you want to apply the delay. The dash through option is useful if there are a number of paths that have common sources or destinations. Here is a simple example using the set max and set min delay constraints. The dash from option is used to select which input path the constraint should be applied to. The dash to option targeting out star indicates that the constraint is applied to the paths that go from that input to any of the output ports. For example, the other method of constraining I/O signals is by providing the timing analyzer with information about external delay parameters. With this information, the fitter can place and route the design in a way that satisfies external timing requirements. Let's look at synchronous data inputs first. If the fitter knows about the T sub CO of the external device shown here, as well as the board delays for the clock and data, it can place and route the input register along with the T sub data int and the T sub clock to int paths in such a way as to ensure that the FPGA setup and hold time requirements are met. Looking at synchronous outputs, the fitter again needs to know about board delays, as well as the setup and hold time requirements of the external device that the FPGA is driving. This gives the fitter enough information to place the output register and to route the T sub data int path to adjust the FPGA's T sub CO value in such a way that it guarantees that the external device's setup and hold time requirements are met. To constrain I/O using external delays, use the set input delay or set output delay constraint commands. These commands have -max and -min arguments in a similar manner to the set max delay and set min delay commands. Pairs of these commands are required, one with the -max and the other with the -min, to define a range of external delay. Let's look at a maximum delay first. On the input side, use a maximum delay constraint to specify the maximum amount of time it can take a signal to arrive and still meet the FPGA's setup timer requirement. On the output side, a maximum delay constraint specifies the maximum amount of time available to output a signal and still meet the external device's setup time. The equations listed here take into account the board delay, including any capacitive loading, the clock skew between the clock arriving at the FPGA and the external device, and the clock to out or setup time requirements of the external device to calculate the largest possible external delay value for inputs or outputs. Compare the equations to the schematics of the previous slides to see where the values come from. The computed input or output delay max value is used as the delay value in the constraint. Now we'll look at minimum delay in a similar manner. On the input side, the minimum delay constraint specifies the minimum amount of time a signal should remain active to still meet the FPGA's holding time requirement. For the output, the minimum delay constraint specifies the minimum amount of time the output signal should remain active and still meet the external device's hold time. Again, the equations must take into account the board delay and the clock skew, but also the clock to out or hold time requirements of the external device. This time, the values are selected to calculate the smallest external delay possible. Using the bold equations as a guide should help when determining the values to use for external delay. Here are the options available for the set input delay and set output delay commands. The options are the same for both. The more important options are listed here. In addition to the -max or -min option, you must specify the clock that drives the external device's register on either the input or output side in order to determine which edges to use for the launch and latch edges. Based on the earlier discussion about virtual clocks, the -clock option should always reference a virtual clock. Recall that the virtual clock is the clock used to clock the external device either on the input or on the output, so using this clock as a reference is necessary for correctly establishing the launch and latch edges for I/O timing analysis. The -clock fall option is used if the data is launched or latched on the falling edge of the specified virtual clock at the external device. The -rise and -fall options specify that the external delay should only be applied on the rising or falling edge of the targeted input or output data port. Without -rise or -fall, the delay applies to both edges. Since -max and -min and -rise and -fall are each mutually exclusive to each other, you could have 2 or 4 constraints for each I/O port. Only 2 constraints specifying -max and -min are required if the delay can be applied to both the rising and falling edge of the data. Finally, the -add delay option is required if different delay values are to be applied to the same targeted port. This can occur, for example, if you want separate analyses performed for data launched by the rising edge of a clock versus data launched by the clock's falling edge, as is the case in a double data rate source synchronous interface. Note that in order to fully constrain an I/O port, you must include both a -max and -min delay constraint. If you only specify one or the other, the same value will be used for both max and min, and the tool will display a warning. Set input delay and set output delay constraints can be created using the GUI as shown here. Notice that for the clock name, you can select a clock from a pop-up list. This feature of the GUI is only available once all clocks have been constrained and the netlist updated with those constraints. The other options let you specify the calculated external delay value and the target port or ports for the delay. Remember that you can manually edit the targets and SDC command fields in order to add wildcards. Here's an example of how to use both set input delay and set output delay to fully constrain synchronous I/O. First, the clock named clock is constrained as usual along with virtual clocks named clock VIN and clock VOUT for the upstream and downstream devices respectively. Next, -max and -min set input delay commands constrain the input on the data import referencing the virtual clock VN. The actual external delay values are broken down into their factors using the tickle expression command. For example, for the input max delay highlighted here, the delay is equal to the maximum board delay of 1 nanosecond minus the minimum clock skew of minus 0.5 nanoseconds plus the maximum T sub CO of the external device specified as 5 nanoseconds. The set output delay commands work in a similar manner using the defined equations, but the -clock fall option is used. This is necessary because the output data is clocked in on the falling edge of the virtual clock VOUT at the external device. It may seem complicated at first, but the equations make it easy to specify the correct delay values to ensure that all timing requirements, both internal and external to the FPGA, are met. As before with unconstrained clocks, use the Unconstrained Paths report to look for any unconstrained I/O ports and port paths. Port paths refer to all the fan-out from an input port and all the fan-in to an output port that are considered unconstrained because the input or output port itself is unconstrained. The Unconstrained Paths summary report will indicate the number of unconstrained paths, while the reports in the setup and hold analysis folders show you exactly which paths are considered unconstrained. With all clock and I/O constraints defined in a .sdc file, the Unconstrained Paths Summary report should indicate that the design is now fully constrained. However, you may need to add constraints in addition to the constraints presented so far in order to accurately describe how the design is supposed to work with respect to timing. These special constraints, called timing exceptions, change the way the timing analyzer looks at targeted paths for analysis. First, as discussed earlier, setMax and setMin delay can be used to select an arbitrary delay range for a path. These constraints are included as timing exceptions because using them overrides the default delays that would be selected by the fitter based on the required clock and input or output delay constraints. Next, the setFalsePath and setClockGroups commands tell the timing analyzer to intentionally not perform a timing analysis on certain paths in the design, including those that go between asynchronous clock domains. These commands are also very useful for isolating test or debug logic in a design, as well as for isolating multiple clocks that are never active at the same time, such as those on the output of a clock mux. SetFalsePath can also be used to prevent certain types of analysis from being performed on a targeted path. The setMulticyclePath command is used to change the default launch or latch edge used for either the setup or hold analysis. By default, Timing Analyzer assumes that all data transactions take one clock cycle to reach their destinations. Specifying a multi-cycle path moves the launch or latch edge, loosening the timing by providing extra clock cycles for logic that specifically requires more than one clock cycle to generate a result. A good example of where this might be used would be with the multiplier. If the multiplier requires 2 clock cycles to output a value, there is no way timing can be met with the default of only one clock cycle for a data transaction. Adding a multi-cycle constraint on data going through the multiplier provides the extra clock cycle required by the logic. Timing exceptions are not required to fully constrain a design, but they may be required if the design calls for them. For details and examples on the use of timing exceptions, see the Timing Analyzer chapter in the Intel Quartus Prime handbook. This concludes the Timing Analyzer training. So, to sum things up, timing constraints are very important in any FPGA or CPLD design. To guarantee that your design will meet all timing requirements, you must constrain all paths in the design, but at least the clock and I/O paths. The Timing Analyzer provides an easy-to-use interface for creating SDC constraints and verifying timing with its extensive reporting capabilities. This concludes the final part of this training. If you missed any of the previous parts, you can register for them for free at the link shown here. To learn about additional resources available to help you with using Timing Analyzer, continue to the next slide. For more information about timing analysis and the Timing Analyzer, be sure to read the Timing Analysis Overview and Timing Analyzer chapters in Volume 3 of the Intel Quartus Prime handbook linked here. To learn techniques for closing timing in a design using SDC constraints and Timing Analyzer, see the Timing Closure and Optimization chapter in Volume 2. If you'd like hands-on experience with Timing Analyzer, or you want to learn advanced techniques for closing timing in a design, enroll in any of the Timing Analyzer related instructor-led courses listed here. There are many free online training courses, just like this one, that can help you learn more about timing analysis and timing closure. Use the links here to register for a course or to find more training at the Intel Training website. One last thing. When you registered for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and if you can think of ways that it can be improved.